Hi everyone, my name is Enrique Paillas. It is a pleasure for me to show you for the first time the new measurements of baryon acoustic oscillations and their cosmological implications after 3 years of operations under what we will call Data Release 2. I am grateful for the opportunity to present our DESI results here, and I hope you can all enjoy the talk. Our BAO results from last year caused a bit of a splash in the media and the literature. DESI found tantalizing hints of potential deviations from our standard model of cosmology, the so-called lambda CDM model, suggesting a possible evolution of dark energy over time. And since that release, a lot of people have been wondering about what the new DESI results will tell us about this story, and you are among the first people who will be able to see it now. Before we begin, I'd like to express our gratitude for all of our sponsors and the 72 participant institutions which have made all this work possible. So what I will be showing you in the next few minutes is a large international collaborative effort with participation from scientists across all career stages. During previous talks, my colleagues have shown you the immense capabilities of the first data release from DESI after just 1 year of observations. But in this talk, I'll be revealing the clustering measurements and the cosmological constraints obtained with 3 years of operations within the context of the second data release. After 3 years of operations, DESI has observed over 30 million galaxy and quasar redshifts, 14 million of which are used in this clustering analysis. And compared to DR1, which used roughly 6 million redshifts for the clustering analysis, this new dataset represents a factor of roughly 2.4 improvement in data volume. Here's a visualization of the sky coverage from the DR1 sample from last year, where the coloring represents the number of tiles that cover each region, with redder colors having higher completeness. And I will now transition to the new DR2 dataset, so you can see how much additional sky area is being covered, while also increasing the completeness on the previously observed sky regions. This is probing the expansion history of the universe through measurements of baryon acoustic oscillations. So before the epoch of recombination, the universe behaved like an optically thick primordial plasma that consisted of photons, baryons, and electrons. And the struggle between the force of gravity and the radiative pressure from the photons created these sound waves that propagated through the plasma until the universe was cool enough to recombine hydrogen atoms. And at that point, the universe became transparent to radiation. The baryons stopped feeling the drag of the photons at the so-called baryon drag epoch, and the acoustic waves froze in place. So these ripples eventually provided regions where galaxies would preferentially form later on, and this is what allows us to detect these baryon acoustic oscillations from galaxy surveys such as DESI in the present universe. Measuring the extent of the BAO feature along the line of sight of the observer provides a constraint on RD, which is the sound horizon at the drag epoch, divided by the Hubble distance. On the other hand, measurements of the extent of the BAO feature across the line of sight of the observer provide an estimate of RD over dm, where dm is the Comovy angular diameter distance to the redshift of interest. The main summary statistic we use to extract the BAO feature from galaxies and quasars at redshifts lower than 2 is the galaxy 2-point correlation function, and this essentially quantifies how especially clustered the galaxy distribution is as a function of the scale. And in this figure, the BAO feature shows up as a bump in the correlation function signal around 100 megaparsecs over H. At redshifts higher than 2, DESI also performs BAO measurements from the so-called Lyman Alpha Forest. So this forest is observed as absorption features in the spectra of individual quasars that are produced by relatively low density gas in the intergalactic medium. And this absorption traces the large-scale structure through the relative amount of neutral hydrogen gas at a range of intervening redshifts. And it proves a broad range of scales that go from small scales that are dominated by gas pressure all the way to the large scales that contain the BAO signal. So these forest BAO measurements are based on the combination of two types of correlation functions. So we have the autocorrelation function of the Lyman Alpha Forest itself, which is what's shown on the left. And then we have the cross-correlation function between the forest and the quasars on the right. And you can see how the BAO feature is also imprinted in these summary statistics around 100 megaparsecs over H in both of these figures. To minimize the risk of confirmation bias in our analysis, we used a blinding scheme to conceal the true position of the BAO peak observed from the data until we fixed all choices about our inference pipeline. So for galaxies and quasars at lower redshifts, we applied a blinding at the catalog level, So we modify the galaxy redshifts and weights in a way that mimics a different underlying cosmology. And for the Lyman Alpha Forest, we blinded the data vectors themselves by shifting the BAO peak location in these correlation functions. We perform an exhaustive list of validation tests before we unblinded these measurements. So for galaxies and quasars, this included changes in the choice of data vector, the modeling of the BAO. We tested for imaging systematics, different ways of splitting our catalogs, and so on. In this figure, each column is showing results from different DESI samples, and it's showing how the BAO parameter constraints are responding to each of these changes in the pipeline. These results are presented in detail in the second of our key papers and in this supporting paper, which shows that BAO measurements are remarkably robust against all of these different changes. We perform equally exhaustive validation tests for the Lyman Alpha Forest measurements by testing the methods to estimate the fluctuations in flux, the correlation functions and covariance matrices, as well as different modeling choices and variations in datasets. These tests are described in detail in the first of our two key papers and in the two Lyman Alpha supporting papers that will also be available on the archive. Here is the collection of all DR2 BAO measurements where the different colors represent different data samples. The BAO feature is successfully identified for all of our samples, and the detection significance goes up to 14.7 sigma, which makes it the most precise 3D BAO measurement from any galaxy survey to date. Here is a closer look at the isotropic BAO distances on the left and the transverse versus parallel BAO distance ratio on the right. I have also overlaid the measurements from the first data release with open symbols to highlight how much the error bars have shrunk due to the increased volume of the data. And this increase in precision ranges from 30% to 50% depending on the tracer. We also have this new quasar distance ratio measurement, as the signal to noise ratio of this tracer has now increased sufficiently to perform a two-dimensional BAO fit, measuring the perpendicular and parallel BAO distances separately, something that wasn't possible in DR1. In these figures, we also have a horizontal line at 1, and this line shows the lambda core dark matter model that best fits the DESI measurements. And this best fit model continues to find disagreement with the lambda core dark matter model preferred by the CMB measurements from Planck 2018, which is what's shown by the dashed line. And this is a trend we had already observed in DR1. The cosmological constraints derived from DESI measurements of every tracer are strongly complementary and consistent between each other. So this figure is showing the constraints of the matter density on the y-axis and the Hubble constant times RD in the x-axis. So from low to high redshift, the increase in the effective redshift of the sample induces this counterclockwise shift in the degeneracy direction. And it is a combination of all DESI traces at different redshifts that produces the tightest constraints, which is what's going to be shown by the black contour in the middle. And this is due to the degeneracy breaking in this parameter space. So now that we've gotten a sense of the volume, the quality, and the robustness of the data, let's jump straight to the main results, starting from the constraints we obtained under the standard model of cosmology, the so-called lambda core dark matter model. Compared to our previous results from data release 1, we find a 40% improvement in the precision of omega matter and H0 RD, while also finding great consistency in the recovered constraints. However, the discrepancy with respect to the CMB constraints, which are shown here in pink, have increased from the 1.9 sigma discrepancy we had in DR1 to a 2.3 sigma discrepancy in DR2, under the assumption of the lambda CDM model. As we saw in this previous slide, BAO by itself doesn't constrain H0 separately, but we rather constrain a combination of H0 and the sound horizon at drag RD. We can, however, calibrate this standard ruler by providing external information on RD, and this can be achieved either by directly using the RD constraint derived from CMB fits, or if we want a calibration that is agnostic to the CMB, we can use Big Bang nucleosynthesis information, or BBN for short. So BBN constrains the baryon density, and this baryon density, when combined with with BAO measurements, also allows us to determine RD with high precision. And in fact, this combination of DESI plus BBN provides a 0.8% precision measurement on the Hubble constant that is independent of any CMB information. And this is already comparable in precision from the Planck 2018 CMB measurement. And this is also 28% more precise than what we had for the DR1 dataset. We can in fact improve this constraint even further if we add a prior on the angular acoustic scale theta star as measured by Planck, which is one of the most robust and best measured quantities in cosmology. And this combination yields a 0.7% constraint on H naught. And this is what's being shown by the orange contour in this figure. Here we show the comparison of DESI plus BVN in this omega matter H naught plane relative to the Schu's distance ladder measurements from 2024. Within lambda CDM, we find that the tension between DESI plus BVN and Schu's H naught now stands at 4.5 sigma independent of any CMB information. As the name of the instrument suggests, probing the behavior and the nature of dark energy is one of the primary goals of DESI. The question of perhaps greater interest, and the one that BAO measurements can best illuminate, is the value of the equation of state parameter W and its possible evolution with time. This equation of state, as a reminder, equals to -1 in the standard lambda CDM case. So to examine the potential redshift evolution of this, we will use the so-called CPL parameterization, where we have a W naught parameter that governs the present-day dark energy equation of state, and WA, which modulates the time evolution. So while this form of W of A does not arise directly from an underlying physical model, it is a flexible parameterization that is capable of matching the predictions from observable quantities from a wide range of models that are physically motivated. BAO data from DESI constrain a combination of W naught and WA, and they define a degeneracy direction in this plane, as shown by this figure. This is the result we had from DR1 from last year, and I will now show you what we obtained with DR2. And as you will see in just a minute, the combination of this BAO information with external datasets will allow us to break parameter degeneracies that result in very tight constraints on these two parameters. In DR1, the combination of DESI BAO with CMB information resulted in a 2.6 sigma preference for evolving dark energy, and that's what's being shown by the dashed pink contour here. Now, using the same combination of DESI and CMB for DR2, we find that the significance of the rejection of lambda core dark matter stands at 3.1 sigma, preferring the same quadrant of the parameter space as in the DR1 analysis. Adding information from supernovae distance measurements adds further constraining power. So we have tried different combinations with different type 1A supernovae compilations. So for instance, when combining DESI BAO, CMB, and the Pantheon Plus supernovae sample, the rejection of lambda CDM stands at 2.8 sigma. If we instead combine it with the Union 3 sample, the rejection of lambda CDM stands at 3.8 sigma. And instead, if we combine with dark energy survey Y5 supernovae results, we obtain a 4.2 sigma rejection of the cosmological constant. To assess the robustness of the preference for dynamical dark energy, we have tried different data combinations and selections, which also helps us understand where the information is coming from. For example, rather than combining DESI with the full CMB information, we tried using simple early universe priors on the angular scale of the sun horizon theta star and the physical baryon and cold dark matter densities, while marginalizing over all the other information that depends on late time physics in addition to DESI. And that's what's being shown by the blue contour. And this actually gives very similar posterior constraints on W naught and WA to the full DESI CMB combination, which I will overlay here in pink. So we find that the W naught and WA values that we recover are very stable. As I've shown previously, the tightest constraints come from the combination of DESI BAO, CMB, and supernovae simultaneously. And there has been some debate in the literature about the sensitivity of these combined constraints to potential systematics in the supernovae compilations, especially regarding the consistent calibration of the low redshift and the high redshift supernova counterparts. Here, the dashed contour in the middle is showing the results you get if you exclude the low redshift portion of the supernovae sample and only take the DSY5 supernovae at redshifts larger than 0.1, which is the most uniformly calibrated sample. This naturally degrades the constraining power compared to the full sample, which I will overlay here in green. But the best fit values for W0 and WA still remain far from lambda CDM. And as a reminder, even if we exclude all supernovae data, the statistical significance of the preference for dynamical dark energy still exceeds 3 sigma just from DESI and CMB alone. Another possibility is that CMB constraints suffer from some unknown systematic error. So it is therefore also interesting to consider the constraints that can be obtained independently of the high redshift CMB anchor. The primary role of this high redshift CMB anchor is that it limits the freedom to vary omega matter when fitting the low redshift BAO and supernova distance measurements. And this can be achieved by replacing the CMB with the dark energy survey 3x2 point weak lensing information to obtain a constraint that comes entirely from low redshift cosmological probes. And that's what's shown by the orange contour in the rightmost panel. And we find that this combination favors the same region of the parameter space, although with somewhat larger uncertainties. Now, we'd like to get a better intuition of why these datasets prefer dynamical dark energy. So let us focus on this plot where I am showing the isotropic BAO distance measurements at the top and the supernova distance modulus measurements at the bottom. In both of these plots, the solid line with the gray shading represents the lambda CDM prediction from the Planck CMB measurements. The first thing to note is that DESI measurements clearly prefer lower distances than Planck at redshifts less than 1, as seen from the panel at the top. And while there is a lambda CDM model that fits the DESI data relatively well, shown by the orange line here, this model has a matter density parameter that is lower than the one Planck prefers. The joint fit between DESI and CMB, which is shown now by the blue line, this one has an intermediate omega matter value that ends up being a worse fit to DESI BAO and the CMB. And as you can see from the bottom, it also fails to describe the supernovae data. And of course, there also exists a lambda CDM model that can reasonably fit the supernovae data by themselves. So this is what's shown by the purple line. But this model has a large omega matter value that doesn't align well with the Planck constraints. It's also strongly inconsistent with the DESI data, which prefers an omega matter value that is much lower. And this is for DESY5, but we've found similar trends for Pantheon Plus and the Union Cree sample. So all these observations are pointing to the fact that lambda CDM is struggling to consistently fit all these 3 datasets taken together, BAO, CMB, and supernovae. And one way to address this tension is to adopt a model with more flexibility in the background expansion. So we can start with the WCDM model, which assumes a constant equation of state that is allowed to vary as a free parameter, but it's not necessarily equal to -1, as it's the case for the cosmological concept. Here the cyan dotted lines show the WCDM model that best fits DESI CMB and the DESY5. And the issue is that the high Z anchor from the CMB doesn't allow enough redshift evolution for this model to provide a good fit to the BAO and supernovae data at low redshifts. And it actually only performs slightly better than the Planck lambda CDM model. On the other hand, the W0 WA model does have sufficient flexibility to simultaneously achieve good fits to all 3 datasets. So the green dashed and the red dashed curves in these panels are showing the W0 WA model that best fits DESI plus DESY5 and DESI plus CMB plus DESY5 respectively. And as you can see, these 2 lines are barely distinguishable from each other. And this is telling us that the best fit model that BAO and supernovae data prefers automatically also provides a good fit to the CMB data. And simultaneously, this also resolves the mismatch in omega matter between DESI and CMB that persisted in the lambda CDM framework. We can map these best fit W0 WA models into a plot of the dark energy equation of state as a function of redshift. That's what's being shown in the top panel. and the energy density as a function of redshift, which is what's shown in the bottom. And what we observe is that the dark energy density had been increasing as the universe evolved. It reached a maximum around redshift 0.5, and that's the point where the equation of state crosses -1, as seen in the top panel. This crossing is sometimes called the phantom crossing in the literature, and this energy density has been decreasing since that moment. We can also look at this in terms of the deceleration parameter, which quantifies the deceleration rate of the expansion of the universe as a function of redshift. Here, the blue band represents our preferred dynamical dark energy result. That's what's being shown by the blue band. And then the dashed line is the cosmological constant. So we note here that the blue band is crossing zero earlier than lambda CDM, meaning that this best fit doubly not WA model begins acceleration faster than lambda CDM. The acceleration phases reach faster than lambda CDM. However, if you look at the lower redshifts, there was a turnover point. And at the present day, this model is actually accelerating less than the corresponding lambda CDM model. We have a supporting paper on dark energy that concentrates on these interpretations and explore parameterizations beyond the W not WA model. So if you are interested, I welcome you to check it on the archive tonight. Another very important major science goal of DESI is to better understand the physics of neutrinos. So we know from terrestrial neutrino oscillation experiments that neutrinos come in different flavors. And they must have a non-zero mass in order to explain the oscillations between these different eigenstates. So as the universe expanded, the primordial neutrinos that were produced before nucleosynthesis gradually lost their kinetic energy. So they behaved as radiation in the early universe, and then they transitioned to non-relativistic matter around a redshift of 100 or so for realistic neutrino masses. Thereafter, influencing the late-time expansion history by contributing to the matter component. So the main effect of massive neutrinos on the CMB is to impact the distance, the angular diameter distance to the surface of last scattering. But this is actually degenerate with the effect of varying other cosmological parameters such as the matter density and H naught, as seen by the correlated constraints from the CMB in this figure. The precise measurement of the matter density from DESI helps by breaking this geometrical degeneracy in the CMB. And given the preference for a low matter density value from DESI, the joint constraint on the sum of neutrino masses ends up being very, very tight under the assumption of lambda CDM. Within the context of this lambda CDM model, the combination of DESI and CMB yields an upper bound on the sum of neutrino masses of 0.0642 eV at 2 sigma confidence, which is actually the tightest upper bound on the sum of neutrino masses to date. Now, this upper bound set from cosmology is getting uncomfortably close to the lower bound of 0.059 EV set by neutrino oscillation experiments under the assumption of the normal neutrino hierarchy, which is what's shown by the pink shaded region here. Now, if you look closely, this posterior, shown by the blue line, resembles the tail of a distribution that would actually peak at negative neutrino masses if it were allowed by the prior. And in fact, it does do that if you allow the model to explore non-physical regions of the parameter space using an effective neutrino masses that is allowed to assume negative values as well as an academic exercise. So given the discrepancy between DESI and CMB under the lambda CDM model, and also given the strong preference for W not WA model dynamical dark energy, as we saw previously, it is natural to consider the effect of allowing the equation of state parameters W naught and WA to vary simultaneously as we change the neutrino mass. And in this scenario, and assuming a positive neutrino mass prior, we find an upper bound of 0.163 eV when combining DESI with CMB. And that's what's being shown by the dashed black line here. And as you can see, the peak of the 1D marginalized posterior is now recovered in the positive mass range. And the constraining power is also significantly relaxed, which relieves some of the tension between DESI and the neutrino oscillation experiments. If you are interested into a deeper dive into this neutrino physics, also check out our neutrino supporting paper, which explores This results in much greater detail than what I've shown here. Overall, we have gathered different pieces of evidence that suggest that the interpretation of different cosmological datasets under the context of lambda CDM faces some challenges. So we find discrepant results between DESI plus BBN and the CMB in the omega matter H0 plane. And at the same time, we find that DESI prefers lower omega matter values than Planck and even lower than the ones that are preferred by supernovae. Also, when assuming a lambda CDM background, the combination of DESI and CMB places the tightest upper bounds on the sum of neutrino masses to date. However, there is an increasing tension with respect to the lower bounds set from terrestrial neutrino experiments. Even more so if we allow our models to explore non-physical regions of the parameter space with negative effective neutrino masses. So all of these things are hinting at a growing incompatibility between different datasets when they're tried to be interpreted under the assumption of the lambda core dark matter model. At the same time, we find evidence for evolving dark energy that has increased with this new dataset. We now find a 3.1 sigma rejection of lambda CDM just from DESI and CMB data, and between 2.8 and up to 4.2 sigma significance when also combining with supernova datasets. This evolving dark energy model also helps to reconcile these tensions that were discussed in the previous bullet points. Overall, unless there is an unknown systematic error associated with one or more of these datasets, it is clear that lambda CDM is being challenged by the combination of DESI BAO with other measurements, and that dynamical dark energy offers a possible solution to this puzzle. Thank you very much for listening to me.